Welcome everybody. I'm Amit Apte. I'm a faculty at ICTS. Welcome you to the public lecture. I think one of the first public lectures on mathematics certainly in the campus. So I will first ask Rajesh Gopakumar, Director of ICTS, to talk a bit about ICTS.
Thanks, Amit. Well, I won't talk very much about ICTS. I'll just welcome you all. And I'll just correct Amit a little. I think this is the second public lecture on mathematics we are having. We had Ken Ono's lecture on Ramanujan a few weeks ago. But this is actually the fourth public lecture we are having at ICTS. We've had the one on Ramanujan, and we had two in physics, one on the astronomy and the square kilometer array in South Africa, very fascinating lecture. Another on times arrow by Joel Lebowitz, an expert in statistical mechanics. So very broad canvas talks, and that's what ICTS public lectures are meant to be. We would like to get not just, of course, scientists who hear a lot of lectures, but people from the public interested in some of the big questions in science, some of the big outstanding problems, and hopefully get enthused by it, especially if they're students, and so on. So this is very much a part of ICTS's mission to organize these activities. And we, now that we have our campus, we hope to accelerate this and have a large number of such events. We realize that it's a little far away from many of you who have come, but we try to arrange transport and we'll publicize it and so on. So especially if you're coming in a group from a college or another institution, please let us know beforehand and we can try to facilitate your transport here, especially if there's a sort of a group coming. So yeah, we would very much like your involvement. And I see that it's great to see that all the extra chairs and so on are being used. I think soon we'll have to move our public lectures really to the big auditorium and so that we can accommodate everyone. So about ICTS, well, I won't say very much except other than the outreach component of our mission. We organize programs, and there have been a number of programs going on since we moved to the campus on a wide variety of topics. Just last week, we have currently going on a program on information processing in biological systems. We just finished a program on condensed matter physics and quantum field theory. Previous week was a program on macroeconomics and finance. So a wide variety of topics that ICTS covers. So to live up to its name of being an international center, we really have international level programs and a high amount of participation from around the world. So that's the sort of the second component of ICTS's mission. And of course, we have finally our own in-house research, small but very high quality. People like Amit and so on, who work in various areas of mathematics, theoretical physics, and biology. So that's in a nutshell what ICTS is. So without much more, taking more of your time, I'll sort of pass it on to Amit, who will, I guess, introduce the speaker.
Okay, so I guess first announcement, turn off your mobiles, I guess, and if you put them on vibration, don't put it on a hard surface. It makes a lot of noise and makes actually more noise than. Okay, so I would like to introduce Professor Edriss Titi, who is the speaker today. He is basically a very distinguished and leading scientist studying partial differential equations, the kind of models that come up while studying geophysical phenomena, turbulence, engineering applications, and he So his research really combines deep mathematical analysis and applications. He works on both the analytical aspects and the computational aspects of these problems. He has worked a lot on Euler Navier-Stokes equations, about which he will talk today, and but also on a variety of other types of partial differential equations, including aspects of control theory and nonlinear fiber optics, various applications. So he currently is a he holds a Owen Professorship of Mathematics at Texas A&M University, and earlier he was at University of California at Irvine. He's also a faculty at the Weizmann Institute, which some of you probably know about, and he has won several awards for his work, including the Humboldt Research Award from the Humboldt Foundation. He has won the Society for Industrial and Applied Mathematics prize for the best paper in partial differential equations. He is also a fellow of SIAM. He is also a fellow of the American Mathematical Society, and he has won the prize for the Science Without Boundaries fellowship from Brazil. I hope he visits India more often. This is his first visit to India. And I would like to welcome Professor Edriss Titi to give his talk by following the tradition of ICTS by presenting him with a memento. And I would request Professor Roddam Narasimha, whom most of you will probably know, to present the memento to him. Professor Narasimha.
Thank you very much. Thank you, thank you, thank you. Thank you, thank you. It's heavy.
I do not know what is inside it, so.
No, maybe they will charge me access package on my way out, so.
Exactly. Okay, so it's all yours, Edriss.
Okay, thank you very much for the invitation, and it's really pleasure and honor to be here. This is, as it's been said, this is my first visit to India, and certainly I hope not the last, maybe just an opening of a few other visits in the future. I was told or warned that a few colleges or universities contacted my friend Amit and others about students would like to attend this lecture. First of all, I'm honored and I'm very happy that young people are taking interest in research even early in their life and their career. And therefore, I would like to basically take advantage of their presence to use you or abuse you every time. I would like to simplify my talk. And I would like to apologize to the experts. Maybe they will find something new in my lecture. Maybe they will not find anything new in my lecture. Maybe I'm going to exaggerate once in a while. This is for me a public talk, so it is not a mathematical talk, so it is a show. And as a result, you know, like basically cartoonist, you have to exaggerate with everything. So I will hope that some of the experts will not really go after every epsilon and delta in my proof. So epsilon be small enough, like 100 or something like that. So. In any case, so there is going to be a message for the students in particular, and rather I say it right now. We all talk about mathematics. People talk applied mathematics or pure mathematics. Actually, in my opinion, there is one thing, is mathematics. There's no pure, no applied. I don't care if you're doing topology, geometry, differential equation, control theory, asymptotic expansion. It's all under one umbrella. Computer science, let's basically emphasize that. It's all mathematics. And you will see actually in my lecture today that in fact, some of the most creative and breakthrough results in fluid mechanics coming from completely different area of mathematics, which is the experts in PDEs will have never thought about it, and it made some breakthrough, and we will talk about that when I get to the lecture. I will try to be a little bit slow sometimes, and sometimes I'm going to go fast, so I have to do some details just to impress you that I really know something deep. So, but nonetheless, lots of the stuff is going to be more or less like a easy talk, and I'll be very happy to entertain questions after the lecture, even personally, privately. I know some students will basically be waiting until all the big guys finish their questions and then they come and ask. So don't be shy. Come and ask me even after the big guys are gone. I'll be here and I'll be very happy to entertain the equations. And I welcome you here, and I'm very happy. I see lots of young faces, so this is very, very, you have a big mission. You have to solve the problem that we don't know how to solve. So, and it starts already here. You have no excuse. By the end of this hour, I certify you experts in Navier-Stokes equation, and therefore you are part of the competition. All right. I need eventually a piece of paper, just one page for later, not for now, that I will need to destroy. You don't mind if I destroy it? Sure. Okay, well, okay, then. This is your introduction. Very good, thank you very much. It's my introduction, okay, I can destroy my introduction. Can you give me the conclusion one? Okay, so let me ask the following question. What title do you give to this picture? Love. What title do you give to this picture? Love, you know, see two guys, you know. So. What title do you give to this picture? What title do you give to this picture? It's behind me, isn't it? What title do you give to this picture? Turbulence. Ladies and gentlemen, as you may have noticed, we are now making our initial descent. So this is an airplane. So it's very turbulent weather. So this is turbulence. Now I show you some pictures, and in some sense you managed to identify or give title to these pictures. And therefore the question that what is love, fear, turbulence, and so on and so forth? And the answer is very simple. You will know it when you see it. You know, we don't have quantifier, we don't have a theory, we don't have like a theorem or a litmus test to can tell you, oh, this is love, oh, this is fear, oh, this is turbulence. You'll be in a situation, you will know it. And everybody who took an airplane knows that when the ride is smooth and knows when the ride is rough. Okay, so setting joke aside, even though there isn't much really difference from reality about what's happening here, the goal of basically we as mathematicians, here's some pictures of turbulence even by artists, like Leonardo da Vinci. There is some experiments and numerics about turbulence. You can see that this phenomena, which is very complex, very complicated, and why complicated now start to becoming intimate with the picture. I look at the picture, I look, oh, this is turbulence, it looks complicated. But now, okay, now, all right, complicated, fine, now let's roll our sleeves, start digging. What do you mean complicated? One of the issues you see that there's so many phenomena at different scales. There's larger scales, there's smaller scales, and they are all interacting with each other. So it's involving many, many, many scales, spatial scales and time scales, and they're all interact dynamically with each other. And especially the global scales, like basically what's happening here is related to what's happening here. It's global versus local, okay? And this is because of the pressure. And this makes that basically this phenomena controlled in a global way. You do some disturbance here, it might affect things here. And therefore one has to be careful, and that's basically why the whole problem is complicated, because involving so many scales. Again, I'm not getting technical, I'm just giving you the picture and tell you why it is complicated. Of course, you talk to engineer, they give you one scenario, you talk to physicists, give you one scenario, to mathematician will give you a different scenario, but they are all the same, they are all right in that sense, because everybody sees it from different glasses, which is remind me of a joke about a rabbi, that the husband and wife go to the rabbi, and they are in fight. So the husband tells the story, and then the rabbi says to the husband, you know what, you are right. Then the wife tells exactly opposite story. You look at her and say, you know what, you are right. Then the pupil there, the student of the rabbi, ask him, you look, the husband said something, the wife said something different, and you told to both of them that they are right. How could that be right? He says, you know what, you are also right. So therefore, they are all right from their own perspective, and so on and so forth. So let us basically go ahead. So this is a very complex phenomena, since it involves a wide range of dynamically interacting spatial and temporal scales, as we have seen in the pictures. Now the question, can one develop a mathematical framework to understand this complex phenomena? Mathematics, in some sense, in all the history, and I don't want to go to the philosophy much, but we have to touch upon it. It always, many fields of mathematics, the way we know it now, it's initially started from somebody asking a question, simple question. It could be naive or not naive, it doesn't matter. And then while you're trying to understand the question and generalize it, you develop a framework in order to understand it. The question, can we develop mathematical framework to understand this phenomenon of turbulence? Okay? And we know that we have so many stories of that type. So the point is, regardless of the success of solving this problem, in mathematics, the journey of solving a problem and the tools that are developed to solve it become more interesting than the problem itself. You know, if somebody tells you like, well, Fermat's last theorem, if I take a taxi driver and it says I'm professor work in number theory, and I'm trying to prove, is it the solution for the equation x to the power n plus y to the power n equals z to the power n, and I'm paid big salary to do that thing. Why do you think the taxi driver should care? Okay? So the point is that the problem is very simple, but as we said, sometimes even though we formulate problem which is simple, the journey of trying to solve it, developing so many tools that they're becoming more important, and application even becoming more important than the question that gave rise to them. And that's basically could be the situation, even though we know that in turbulence and in fluids, there is more applications waiting in line in order to understand what's happening. So, but what I'm saying is, for us as mathematicians, we don't need to justify why we are asking these questions and why we are interested. We are interested because we are curious to know, and that's sufficient. And we proved along the history of humankind that we mathematicians ask interesting questions and we delivered. Okay? So in that sense, we don't need to prove anything to anybody why we are asking questions and so on and so forth. At least this is my point of view. So why do we want to understand turbulence? So this is in order to control onset of turbulence, to either suppress it or trigger it. Why want to control it? Because we human beings are control freaks. We like to control everything, okay? So we would like to control it. What do you mean by control it? Sometimes I want to suppress turbulence, and we know that if you're on the airplane, we don't want to have turbulent ride, okay? So we'd like to suppress that. But we would like also to trigger it. When do I want to trigger turbulence? Well, many times it's important to have, in industry, to have turbulent flows to do things, okay? One of them is mixing, for example, in combustion theory for the engine in order to fuel, to burn completely as much as possible. Better the fuel to be very turbulent, the fluid to be very turbulent in order to mix very well, so the burner will be most efficient, etc. But there is some example which is interesting, which was told to me by a very good friend of mine in chemical engineering, and the problem is the following. You have certain gas that you would like to dispose it because it is very poisonous, and you don't know how to get rid of it. You don't want it to go outside, but then it goes out of a chimney. Here's the chimney in some big industrial factory, whatever. You would like to dispose it, but when it's gone, it's gone. How do you do it? How can you collect it? You cannot collect the gas, in some sense. So one way to collect the gas is basically on the side of the chimney here. You pour a very thin film of some chemical which is very interactive with this gas. And then once this thin film of fluid comes down, you can collect it. And the whole idea is you want it to have interaction as much as possible between these fluids and the gas coming. And we know that the larger the wrinkleness or the touch between the two, the higher the reaction rate, and therefore you dispose as much as possible of the gas. And therefore, when you pour this fluid down here, you want it to be turbulent. So you want to trigger turbulence. So turbulence is not always a bad guy. When I was a kid, I always, in physics, in the 9th grade, when we talked about Newton's laws, there is this force and that force, and there's always the bad force, the friction, which goes against the motion. I always thought about friction something bad. Well, I mean, without friction, we couldn't walk, can't we? So it's not always a bad thing. So they have to think turbulence is not always the enemy. Sometimes I need turbulence in order to get things to be done properly. So there are many examples, I say, in industry and in science and engineering supporting this task of why we need to understand turbulence. So now that I gave you this general introduction about turbulence, what's the mathematical point? There is commonly believed that the equation that governs fluid motion, incompressible fluid motion. Now, for the students who do not know what's the difference between compressible and incompressible, it is a little bit, in some sense, delicate, but there is some cases, there is some kind of like criteria. If the motion is very fast, then we can consider the fluid to be like compressible. And if it is not very fast, the motion not very fast, then we can consider it to be incompressible. So I said very fast and very slow. In comparison to the what? To the speed of the ant, or to my walking, or comparison to what? Very fast and not very fast. To give you an example, so you can really think about it, commercial airplanes are considered not very fast, while aircrafts, the fighters, jets, are considered very fast, because one can go with the speed of sound, while the other one is way below the speed of sound. So fast or not fast is in comparison to the speed of sound. So we're going to talk about fluid motion, which is, with the comparison to the speed of sound, is very small, and therefore we're going to consider the equation of motion of incompressible fluid. The first equation here, this is called the Navier-Stokes equation. I don't want to go to the history. There's a lot of things I'm going to talk about. Unfortunately, I cannot cover all the things I want to talk about, but I would like to focus mostly about the singularity, because that's where there's $1 million. Okay, so those who came here to win $1 million, there's $1 million waiting outside for you to get it. But I hope before we solve it will not be equivalent to 1 million rupees, you see? So, so let's wait and see. So this is the first equation of the equations called the Navier-Stokes. The first equation is the conservation of momentum. This is Newton's second law. U is the velocity field, rho 0 is the density of the fluid, and this is the evolution equation of the acceleration, if you want, which is Newton's second law. This term, the U, the three components of the velocity are unknown, as well as the pressure is also unknown, which is a scalar. So I have four unknowns in the Navier-Stokes equation, the three components of the velocity and the pressure. Now, this is vectorial equation, and therefore I have three equations. And this is the incompressibility condition divergence of U equal to 0. What means incompressibility? This means if you take a parcel of fluid, when it's moving, it doesn't change its volume. That's what means it's incompressible. Okay? So now I'm going to assume that the fluid is driven by some force. This is a mathematical hypothesis, let me tell you in advance. Or if you want, could be mathematical physicist hypothesis, because usually the way we drive a fluid is by the boundary. If I put like a pipe and put fluid in it, in order to make it move, I move the pipe from the outside because it's viscous, so it is stuck to the boundary, so the friction in some sense makes it start moving. So usually we drive fluid by the boundaries, or by pressure gradients, or by coupling the fluids to other things. For example, I put like fluid and heat it from the bottom and cool it from the top. So therefore there is buoyancy and you can steer the circulation. In fact, that's the most relevant model for ocean dynamics and for climate dynamics and for weather prediction, etc., because it's coupling between the temperature and the velocity. Or in plasma in astrophysics, it's combination, because it's like basically ionized fluids, and because there's magnetic field, therefore it's coupling with the magnetic field. So therefore this forcing is in some sense usually coming from coupling with something. To give you an example, this is an equation called the Rayleigh-Benard or Boussinesq equation. This is again the conservation of momentum. And if I'm at the scale of planet, this is the Coriolis force, because I live in a rotating Earth. If I would like to see what happens to the ocean dynamics or to the atmosphere dynamics at scale of the planet. And this is the buoyancy coming from the heating from the bottom, cooling from the top. What heats the weather from the bottom and the top? Come on, heating. You talk about heating. Heating, I know when you put water in the stove, you heat and therefore water is boiling. Believe it or not, the ocean, because there are students here, so after the ocean is heating the weather. How so? The temperature in the stratosphere is like minus 50 Celsius. And the temperature in the or maybe even less than that. And the temperature of the ocean is like, say, 12, 15 Celsius. So there's a big difference between them, over 65, 70 degrees. That's a big difference. So it's like basically what's important is the gradient. And that's why the ocean is, in some sense, heating. And that's why, for example, in climate model, the eye is always on the temperature of the ocean. Because if you change the temperature, how much you are heating, things could be changed. And there is a phenomena, for example, which is we suffer from it in California all the time, called the El Nino, because there is certain currents of the ocean, hot water, surfacing once in a while, like once every 9 to 13 years. Then it surfaces, and therefore the temperature of the ocean become much hotter, and therefore have storms and all kind of like problems of that sort. So therefore, this is basically an example just to keep in mind about what we are having. This is the incompressibility, and usually because you have temperature, this is the equation of transport for the temperature. So this is the Navier-Stokes coupled with the temperature, because the temperature is advected, because the temperature is also carried with the fluid. So then usually Navier-Stokes does not come, as I mentioned, by itself. It comes coupled to somebody. But understanding the mathematical features of this equation mathematically, if there is singularity or nice equation or not, or the Navier-Stokes, is basically the same. We are in the same boat. Okay? So therefore, let's focus on the Navier-Stokes equation in order to understand what's happening here. So what happens what is the difference between an ordinary differential equation and evolution partial differential equations? We had like Navier-Stokes, which is a partial differential equation, and we have an ordinary differential equation. They are all differential equations. What's really the difference between what we call ODE and PDE? Of course, there's many answers. I don't want to basically, nobody is going to be tested, but here is basically some place where students have to basically listen, because it's conceptually. Now, what happens when you are talking about ordinary differential equation? So you're looking for a vector field or trajectory moving in Rn. So time is changing, and therefore we have a vector living in Rn, which is changing. So the solution is a trajectory in Rn. Now what happens when we talk about partial differential equations? For every time you have a function of x. For every time you have a function x. For every time you have a function of x. This means the solution is a trajectory of functions. Therefore, the space where the trajectory lives is a space of functions. The space of functions is infinite dimensional. So what's the difference between Rn, which is finite dimensional, and the spaces of functions, which is infinite dimensional? How big is the difference? It's infinite. So the difference between PDEs and ODEs is that in one case we deal with finite dimensional space, where they live, where the solution live, while the other case we are basically dealing with infinite dimensional spaces. Okay? Now, what is really the difference between finite dimensional spaces and infinite dimensional spaces? This is, I said, in ODE, you have a solution which values n. In PDEs, function is x, so with values which is in infinite dimensional space. So what's the difference between finite dimensional and infinite dimensional spaces? A major difference between finite and infinite dimensional spaces they are measured, there are many, many differences. That Bolzano-Weierstrass theorem, everybody knows, because I said, somebody warned me yesterday that there are students, so I have to change my slides. Everybody knows Bolzano-Weierstrass, that if you have basically a bounded sequence has subsequence converging. In infinite dimensional spaces, if you have a sequence which is bounded, we don't know if it's converging in the topology of the space. And this is a big difference. By the way, many theorems that we prove in calculus rely on Bolzano-Weierstrass. For example, why a continuous function in a compact set has a maximum. Without the Bolzano-Weierstrass property, I cannot prove it. In fact, some distinguished mathematicians gave wrong proof because they thought that they have the equivalent of Bolzano-Weierstrass. And one of those big distinguished guys was Riemann, in the proof of Riemann mapping theorem. He basically had a functional that would like to look to the maximum. He assumed that the maximum exists. You have functional, you would like to maximize it in certain space. How do you know the maximum exists? So you have to prove first that something exists. Otherwise, you could get you wrong answers. And all right, so how can I give you that? Well, I like to toy with certain things. So I would like to compute the following number. You bear with me. I think probably you know this example. So let me compute this number. The number x, which is equal 1 plus 2 plus 4 plus 8. You know how to continue. 2 to the power n and so on and so forth. I would like to compute this number. Okay? So how do I compute it? X minus 1 equals 2 plus 4 plus 8, etc., which is 2 times 1 plus 2 plus 4 plus etc., which is 2x. Therefore, 2x equals x minus 1. Conclusion, x equals minus 1. I found x. Okay? So we cannot just basically assume there is an answer to the equation, find it. Okay? We have to prove existence of an answer and then develop tools to compute it. And this is one of the issues when people try to compute on the computer. How do I solve an equation? How do you know there is a solution? And what you get is a garbage, because garbage in, garbage out. Look, I mean, I computed the answer to this number. I found that x equals to minus 1 against all odds, even the right-hand side, all positive numbers. Okay? So therefore, one has to be careful. So therefore, the difference between PDEs and ODEs, again, I'm using the students as as an excuse, is basically this very important theorem about Bolzano-Weierstrass, and the norms are not equivalent. In finite dimensional spaces, all the norms are equivalent. But in infinite dimensional spaces, that's not correct. The norms are not equivalent. Aha. This means if you have an ODE and you show one norm of the solution does not becomes infinite, does not blow up, this means all the norms do not blow up. You set the case, you are done. But in PDEs, if you show, for example, that the energy or the L2 norm of the solution does not blow up, it does not mean the L infinity does not blow up, or the L2 norm of the gradient, or anything like that. And therefore, which norm I need to track is part of the problem. In other words, the difference between ODEs and PDEs is basically that the space where the solution lives in ODEs is Rn is given in advance, and I cannot play with that. But in PDEs, the space where I search for solution is part of the problem. I have to design the space where I search for the. That's why it is a little bit more technical and more interesting. And that's why people say, oh, I can prove a solution of this equation in this kind of space or in that kind of space. Okay, let's go ahead. So let me introduce the Sobolev spaces for those who do not know Sobolev spaces in the periodic boundary condition. It's all the functions which are periodic, such that the Fourier coefficients of this function are decaying faster than k squared to the power s, which means that when s is very, very large, the Fourier coefficients have decayed very fast for this series to converge. What's Fourier series? Fourier series is for every function, oscillatory function of frequency k, I give a weight. So the more oscillatory the function, the more wrinkling, the worse is the function. Therefore, if the coefficient is smaller and smaller for the more wrinkling function, the function is smoother and smoother. And this is the idea behind Sobolev embedding theorem. Like if S is very, very large, the space of functions is nicer and nicer. Why we like to deal with Sobolev spaces? Because they are Hilbert spaces, and we can use tools of function analysis. Instead of talking about maximum and minimum and continuous function and Hölder continuous function and so on and so forth. So we can use tools of function analysis. And this is the space, the Sobolev spaces. So again, this is the Navier-Stokes equation. I would like to see what's happening with this equation. Do I have existence, uniqueness? What could go wrong? Which norm could go wrong? And I'm going to do everything formal. Why formal? Because I have to justify every step. Otherwise, I will come into the case of this one. Because if I do this formal, I can do conclusion x equals to -1, which is wrong. Okay, so you have to justify it. But let me do it formally, at least at the very beginning. So I'm assuming that the density equals to 1, the spatial average of the initial data and the force is 0, which means the spatial average is 0. This gives me some inequality. Again, now I'm going to go a little bit fast, so you don't need to follow with all the details, but I'm going to just show you. There's some inequality called the Poincaré inequality under this boundary condition, namely that the L2 norm less than the gradient. This inequality is not correct in general, because if you take a constant function, the right-hand side is 0, the left-hand side is not 0. Aha, but I assume that the average of the function is 0. So the only constant function with average 0 is 0. So I can feel good. So there's no violation here. So one has to use, in some sense, the Poincaré inequality. So if you multiply by U, and you basically formally you get the energy bound, that the L2 norm of the function satisfying this relationship. I just multiplied by U. Now I use the fact that it's incompressible. I look at this term, you integrate by parts. You use some theorem called Stokes theorem or Green theorem or somebody's theorem. And then integrate by parts here, the gradient comes here, become divergence, because divergence is equal to 0. Then one conclude that basically that these terms are equal to 0. So these terms disappear. And as well, that the energy balance you have like that. Again, this is formal, because let me tell you, in three-dimensional Navier-Stokes, we don't know that this is always correct. This is already one problem, okay? To justify this all the time is not really easy. And it's not even, we don't know if it's correct. Okay, so that basically you would know that at this technical level, there is already, at this very elementary level, there are some issues. Okay, now basically you use here Cauchy-Schwarz, and then you use a Poincaré, and then you use Young's inequality, which tells you that the product of things are less than the sum. You get this relationship for the energy, and then from here you basically use Poincaré inequality again, and then you show that the L2 norm of the function is bounded by this quantity. The right-hand side is always finite. It just tells you that the kinetic energy of the fluid does not grow indefinitely. It is basically, you put energy through the forcing, but you kill it through the viscosity, which is internal friction in the fluid. And as a result, the energy remains finite. But also from this relationship, if I integrate this in time from 0 to t, you discover that the integral of this in time is also bounded, depending on the initial value. So I have two norms which are basically finite. The maximum in time of the L2 in space, and the average of time of the gradient in space. Notice this infinite dimensional space's norms are not equivalent. So believe me, every a priori estimate of this type will play a role. It's important. So this is basically a priori estimate on the solution that one can establish in some sense. And this has been sufficient for Monsieur Jean Leray already in the 30s to basically to show for every t there exists a weak solution for the Navier-Stokes equation, namely continuous in time with value in 2 and basic and average in time in h1. Notice I says in the sense of distribution. For those of you who know what means the sense of distribution, you should realize there is a conflict between sense of distribution and the date, because the sense of distribution did not exist in 1932. This tells you that basically Jean Leray was a genius. He didn't need what's going to come later to make sense of the equation. Okay? So he made sense of the equation in sense of distribution before the sense of distribution. But this is a weak solution. Then what happens? The question is of the uniqueness of weak solutions of the three-dimensional Navier-Stokes is still an open. Are these solutions unique or not unique? And it's an open question. It is very difficult. So do the solution of the existence of the Navier-Stokes exist? The answer, yes. Are they unique? We don't know. It's an open question. In fact, Jean Leray, who basically was very full of himself and he knew what he's doing, because he couldn't prove the uniqueness of this weak solution, he thought, you know what? Maybe the lack of uniqueness of this weak solution is intimately related to the phenomenon of turbulence. If I do an experiment with some initial data, and maybe if I come after 1 hour do the same experiment with the same initial data, why should I get the same solution? Especially if the solution or the initial data is not smooth, like in L2. Okay? So that's why he called them in French turbulent solutions. So do we have existence? Yes. Do we have uniqueness of weak solution? We don't know. Am I afraid of non-uniqueness? Well, frankly, I'm not afraid of non-uniqueness, and this will become clear later, what we talk about. We are obsessed with this uniqueness because we, mathematicians, different than physicists, categorically, in the way we think, we like everything to be nice. We like to prove everything regular and beautiful and smooth. And everything is nice. No trouble. We don't like troubles. Physicists, to the contrary, they like troubles. If there is no criticality, if there is no phase transition, if there is no boom in the lab, they don't care. They are after these kind of like singularities. They are after these kind of like phenomenon, which is transition. And that's why they want to see singularity if possible, or to see something like that. Okay? So therefore, the lack of uniqueness, maybe of the weak solution, could be related in some sense to what physicists are talking about, namely the lack of uniqueness. And therefore, maybe we should not talk about one solution, but about ensemble of solutions. And we should talk about the probability distribution of these solutions and so on and so forth. And I'm going to touch upon this in a minute. Okay? Okay, so now what happens if I look about stronger solution, if I demand the initial data to be nicer? So I want the solution not to be continuous in L2, but in the space H1, in the Sobolev space H1. Namely, I need to look to the gradient of U and show that this is a continuous function or a bounded function. Because of the incompressibility, the L2 norm of the gradient is the same like the L2 norm of the curl, because divergence U equal to 0. And therefore, this quantity, which is the L2 norm of the curl, which is the vorticity, formally satisfying this relationship. Again, when you integrate by parts, you observe that this is equal to 0 because of the incompressibility. But now we have to face the nonlinearity. And to face the nonlinearity, I have to use, basically, I use Cauchy-Schwarz for the nonlinearity and Young's inequality. But now I need to deal with the nonlinear term. I need to estimate this term. So how do we estimate this term? I don't know anything but Holder inequality. I never learned anything about harmonic analysis or fancy spaces, etc., etc. Maybe that's where the key for all these issues, I don't know. But I'm going to do something very simple. So I'm going to use examples of Holder inequalities. For example, I'm going to put L4 norm on the first term, L4 norm in the second term, L2 norm on the last term. Because quarter plus 1/2, I checked them this morning, they were equal to 1. Okay? So therefore, this is an equality. I don't like L4. I don't like Banach spaces. I like Hilbert spaces. Why? Because I do inner products, etc., etc. When you don't like some spaces, what do you do? Like we don't like certain currency, you cache it. you basically exchange it. So I need to exchange some money or some currency into different kind of currencies. This is called interpolation inequalities. Okay? So let's basically see. I would like to look what's happened with L4. I discovered that the L4 norm is the L2 norm to the 1/2 and the gradient to the 1/2 in 2 dimensions. While in 3 dimensions is the L2 to the 1/4 and the gradient to the 3/4. And let me tell the students already here, this is the transparency. If you want to make progress in Navier-Stokes, is maybe here. That's what distinguishes why in 2 dimensions everything is nice and dandy, and why in 3 dimensions we are really, that's where I lost my hair. Okay? It is exactly in 2 dimensions 1/2, 1/2. In 3 dimensions is 1/4, 3/4. These 3/4 is the killer. Because I know that the L2 norm of the solution under control, the gradient that I want to control. So therefore, I would like as much as possible power on L2 and less on the gradient. And this 3/4 in 3 dimensions kills me. So then a smart student comes to you and says, oh, professor, can I basically try to prove these calculus inequalities in 3 dimensions and improve these 3/4 to make it less than 3/4? Like, for example, 1/2 and log of something. Now, we mathematicians, you'd like to prove inequality, you basically try to give direct proof. And after 6 months, the student is not succeeding. You say, you know what? Maybe you can go and find a counter example. And then the guy spends another 6 months or a year, then comes with a counter example, say this inequality cannot be improved. What can I do after we wasted 1.5 years? You cannot give him a thesis for that. And now I'm going to put the hat of a physicist or a hat of an applied mathematician or whatever you want to call it. Can we improve this inequality, 1/4 and 3/4? And why not? The answer is no, but the question is why. I would like to give you basically just rule of the thumb. In American English, or maybe also in English, I don't know, they say you cannot compare apples and oranges. You compare apples with apples and oranges and oranges. You look to the units or the dimensions in the left-hand side and the dimensions in the right-hand side. The only way you can fit the dimensions in 2 dimensions of the left-hand side, right-hand side is with powers 1/2. And 3 dimensions, 1/4, 3/4. You cannot break the laws of physics. You cannot compare kilogram with meter. And that's why, basically, the only way this inequality works, if the constant is dimensionless, is with 1/4, 3/4. Don't really even try. Some people call this scaling argument, whatever you want to call it, but you don't need really to give counterexample. Okay? All right, so what happens in 2 dimensions when you put the 1/2, 1/2? In fact, one can show that in this case, y, which is the gradient satisfying this inequality, which is a Riccati type of inequality. If you integrate this inequality, you show that only for short time y is finite. But I have a joker at hand, that the integral of y is finite, namely the integral of the gradient square. Therefore, you can take this y square, split it into y times y, and multiply by the integrating factor, which is e to the integral of y. Because the integral is finite, therefore the integrating factor is finite, and this gives you that y remains finite. And by this, I can certify you that you know everything you need to know about 2D Navier-Stokes equation. You have global existence in 2 dimensions because it's this y square. Now, what happens in 2 dimensions? We have global existence, uniqueness of weak solutions, finite dimensional global attractor, which is something which is I don't want to talk about at the moment. So now, what happens in 3 dimensions? In 3 dimensions, if you basically do estimates of this type, you discover that basically that y is satisfying L6 to the power 4. And as a result, this y is less or equal than this integral. So the gradient in L2 remains finite all the time if this integral is finite. And then the question, is this integral finite? This is the question, is this integral finite? In fact, this is the $1 million question. We don't know how to show that this integral is finite. If anybody can prove that this integral for solutions of Navier-Stokes is finite for every initial data, this is the $1 million problem. Now, since the Clay Award, of course, many attention was for the Navier-Stokes, and we start being bombarded with papers to referee that somebody say, Eureka, I have a solution. So I start joking about it. Instead of calling the $1 million problems, again, maybe this is politically incorrect in this country, I like to call it the -12 bulls or cows joke or award. Why minus? Because legend has it, and people corrected me that this is not correct story, that when Pythagoras proved his theorem, he went and sacrificed 12 cows and bulls to the gods for being blessed with a great theorem. Okay. So this is basically where the issue. So in the old days, people sacrificed because they were blessed with the theorem. Now we get awards for that, which is nothing wrong with that. We would like awards, we need recognition, and so on and so forth. But this is basically the $1 million question. Okay. So again, the question, is this finite or not? What's so special about 6 and 4? It's just a random, I got it randomly between two kind of like numbers. In fact, there is a whole family of criteria, which is usually known as the Prodi-Serrin criteria, which tells you if the solution is LP in time, LQ in space, when 2 over P plus 3 over Q equals to 1, P between 1 and infinity, then the Navier-Stokes has global existence. Therefore, this is another criteria equivalent to the $1 million problem. Notice the special case when P equals 4, Q equals 6, gives you 1/2 plus 1/2 equals to 1. So this is a particular case. So nothing special about the 6 and 4. Okay? The case of P equals to infinity has been settled about 10 or so years ago by these trois, by Squarizza, Serjegen, and Švirak. Now, there is another way one can look into the L6 using the so-called Sobolev embedding theorem. For those who do not know Sobolev embedding theorem, don't worry about it. That the L6 norm is bounded by the L2 norm of the gradient. In that case, one can show that this y, which is the L2 norm of the gradient square, satisfying y less than y cubed. Notice in 2 dimensions it was y squared. In 3 dimensions, y cubed. But have the average of y is order control. I'm sorry, it's y cubed. This does not help me much. And as a result, all what I can prove is that basically there exists a time t star, depending on the H1 norm of U0, on the forcing, viscosity, and the size of the domain, such that the y remains finite only in this finite. Therefore, this gradient remains finite only for short time. And this is a result of Rayleigh. And that's how basically these are called strong solutions. And only for short time, you can prove existence of strong solution. What's the advantage of strong solution? Because I have already weak solutions. The advantage is because the solutions strong are more regular, when I look to the difference between 2 solutions, I can prove uniqueness because I can put high order norms on one of the solutions. And as a result, we have uniqueness in this particular case. So let me summarize. In 3 dimensions, we have global existence of weak solution, short time existence of strong solutions, uniqueness of strong solutions, the open problems, and again, I say they're almost equivalent, uniqueness of weak solution, and global existence of strong solution. The Millennium problem is for this part, not for this part. But anytime you tackle this, you face this. Every time you tackle this, you face this. In some sense, they are like Siamese brothers or something like that. You know, they are equivalent, not equivalent. They are kind of like intimate and so on and so forth. So this is the open problems. By this, I tell you all what you need to know, and this is already known from the days of Rayleigh, from the 30s. So what happened in a century? What happened essentially, we simplified the proofs, we understand better what the obstacles, and we start dealing with different cases, namely when you have geometry. Rayleigh work was in the whole space. But we know that real fluids takes place in bounded domain. Can we do things in bounded domain? That's what basically was the contribution of Eberhard Hopf and Layzhenskaya and Prodi and Mandar-Lyons, in which basically they dealt with the situation in bounded domains and doing. So there's a lot of machinery and work to simplify and to understand better, and so on and so forth. So I gave you the story of a mathematician about estimates and calculus inequality. By the way, why this is called calculus inequality? Because the proof of these interpolation inequalities, or what's so-called calculus equality, uses nothing more than the fundamental theorem of calculus, namely the integral of the derivative equal to the function. That's where the proof is really starting from. Now, I'd like to put the hat of a physicist and see what there is a difference between 2D and 3D other than this kind of like calculus inequalities. And to understand that, I look to the vorticity. I take the curl of the equation. When you take the curl, you get rid of the pressure. The pressure is a troublemaker for us. The pressure is the non-local term. It's really troublemaker. So when I get rid of that, but if you get rid of it, you know, there is a conservation law of difficulties. There's no free lunch. Okay? So when you take the curl, what happens here, the velocity is transporting the vorticity. What's the relation between this and this? Omega is the curl of u. So to invert and write this in closed form in terms of omega, I have to integrate omega. So therefore, I have to have non-locality in some sense, because integral is a non-local operation. So this is the vorticity formulation. Notice that this is viscosity, this is a transport, and this term is called the vorticity stretching term. Why? Because omega is like derivative of u. So this is like omega times omega. So this is in some sense like acting on omega. It's like omega acting on omega. It's like an avalanche. The rate of change of omega is proportional to itself. Like snowball. The larger the radius, the more it collects. So this is in some sense the troublemaker in the 3D Navier-Stokes equation. In 2 dimensions, this is identically 0, this term. Why? Because the nabla operator is in the xy domain, and omega, because it's curl, in the k direction, in the z direction. So the dot product is 0. So this term is not there. So in 2 dimensions, I have very simple equation. Omega is like a scalar because it's always in the same direction. So in 2 dimensions, the Navier-Stokes is like that. And therefore, omega, because it's scalar in some sense, satisfies the maximum principle. At the point of maxima, the gradient is 0, the Laplacian is negative, so d omega dt goes down. And the minimum, it goes up. So the modulus of omega satisfies the maximum principle, so it's bounded. If this is the L2, if the maximum or the L infinity of omega is bounded, then all the gradients are under control, everything is nice. So that's why in 2D, it's in one transparency, we understand what happens. But in 3D, the monster and the enemy is the vorticity stretching term. So vorticity stretching term, when it's not 0, so if omega is like z, this term is like z squared. Therefore, the balance could be like z dot like z squared, which potentially could lead to blow up, and we don't know. So we are fighting against the vorticity stretching term in the Navier-Stokes equation. Okay? However, my point, and this is what I'm going to mention when I have chance, is basically that this is overrated. So what happens in Euler equation? In Euler equation, the viscosity equal to 0. Now, as I said, there is a whole field of understanding what happens with the limit of viscosity go to 0, namely when the internal friction becoming small. This is called basically that the fluid become more diluted. This means like Reynolds number becoming large. I will talk about Reynolds number later. So what happens at the limit when viscosity go to 0? This is by itself is a mystery. So Euler equation is the case when the viscosity equal to 0. So what happens? Liechtenstein 25, he proved if the initial data in C1 alpha, you have existence of unities for short time. Okay? The same like Navier-Stokes. Now, Eben and Marsden used the modern terminology of HS, and they proved the same thing for Euler equation. Now, Euler equation is like Navier-Stokes, but without viscosity. It's not parabolic equation anymore, and therefore it's a little bit more difficult to deal with. Whether the Navier-Stokes solution converges to Euler equation, there are results by Kato, and later by Peter Constantine, shows that if you don't have physical boundaries, namely if you have a whole space or periodic boundary condition, as long as the solution of Euler exists in some interval, the Navier-Stokes converge to it. Now, what happens if you have physical boundaries? Because this is the real issue. It's an open question, even in 2 dimensions. It's unknown yet if the solution of Navier-Stokes converges to the solution of Euler as viscosity go to 0. And that's why considering Euler as the limit as Reynolds number equal to infinity is a little bit misleading in the infinite dimension, in the domain with physical boundaries. It's an open question. We don't know what happens. And we need to, maybe there's no limit at all. Maybe it's not even an equation. We don't know. It's an open problem. So if some of the graduate students would like to really work on a very challenging problem, even in 2D, do the Navier-Stokes converge to Euler or not in the Dirichlet boundary condition? So this is the classical results. And now the question, does there exist a global weak solution of the 3D Euler equations? Because for Rayleigh proved for Navier-Stokes there are weak solutions. What about Euler? We have strong solution, but what about weak solution? Believe it or not, this was an open question until 2011. We didn't know if Euler equation has weak solutions in 3D. And has been settled by Emil Widman based on the work of his advisor, which is Laszlo Szekehidi from Leipzig. At that time he was at Bonn. And Szekehidi did some work with Delelis, and this is basically important part of what I'm going to talk about later. But I would like to say that he used their tools in order to show there's not only there is weak solution for Euler. Until 2011, we didn't know if there exist. But in 2011, as they say in English, when it rains, it pours. Okay? Not only he proved there exist, but in fact, there are infinitely many of them. Okay? So the answer is yes, but there are infinitely many weak solutions. So now we know more about Euler than Navier-Stokes, because in Euler, we know infinite, but in Navier-Stokes, we have at least one. We don't know if there are more than that. Now, what happens if you have what happens the equivalent of the Serrin-Prodi condition? There is something called the Beale-Kato-Majda. It tells you that as long as the vorticity in L infinity is bounded, then you have existence and uniqueness of solutions of the Navier-Stokes. So if something goes wrong, is this particular for Euler? You don't need to look for higher order derivative. It's a very basic fundamental quantity you can track. And this is important if you would like to search for singularity computationally. So one has to control this particular quantity. So as I said, weak solution for 3D Euler. So as I said, there exists a family, non-uniqueness of a solution of the Cauchy problem, which is a result of Widman. And this has been based on the work of Delelis and Székely-Hidi, showed existence of non-trivial weak solution of 3D equation with compact support in space and time. Let me make a comment on these particular equations. What does it mean? You have infinite many family of solutions of Euler equation with compact support in space and time. Namely, in the past they have been 0, in the future they are 0. And they are confined in this space. Metaphorically, imagine that you have a glass of water. You fill it with water, you go to sleep at night, you put it next to you, so this is the past, the solution is quiet, is 0. Then the solution becoming non-trivial. Then in the middle of the night, the water starts moving. You think there is a ghost in the room, you basically tuck and basically don't do. But then in the morning, the solution becomes 0 again. You wake up, the water is quiet. This is the kind of solution they basically constructed. Like creating energy from no energy. I mean, if such things is physical, then we solve the problem of, the crisis of energy. Okay? So therefore, these solutions, as they sound and we feel them, they are basically non-physical. Yet, they do satisfy the Euler equation. Which means we mathematicians, when we basically have to deal with physical equations, we have to have some kind of additional information about selection mechanism, about who is playing and who is not playing, who is physical, who is not physical. Otherwise, these are equations which should satisfy the equation. These are solutions that satisfy the equation. Now, the point here, which is basically, again, addressing to the students, these guys come from differential geometry. They didn't do the PDEs, they didn't look to the solution by evolution equation, give me initial value, approximate the initial value, approximate the equation, construct solution for the approximation, pass to the limit, none of that. None of that. They came with completely different machinery, okay? So the present proof is not traditional PDE proof. It shares many ideas from the proof of the Nash-Kuiper theorem of invariant of embeddings of surfaces. It uses the formalism of differential inclusions, convex integration, and accumulation of oscillations. This has nothing to do with the PDEs, the way we teach it or we understand it, etc. It's coming from different world. They basically showed that the equations themselves is in some sense like some kind of like convex system with constraint. And they proved existence of sub-solutions, and by adding more and more and more oscillations into it, they reach to the limit, which are basically the solution. That's what I said to the students. I mean, don't tell me I'm doing PDEs or doing applied math. I don't want to learn about differential geometry. You don't know where the idea is going to come from. So what's this Nash-Kuiper? It's basically, suppose you give me some kind of like curve. Some curve in the space. And then I give you a small disk. Can I put this here without changing the length of the curve? Of course, we know how to do it. If it's a rubber, you basically wrinkle it somehow and put it inside. Wrinkling, so therefore the embedding cannot be too smooth. That's why these weak solutions are very bad. This is the idea of the Nash-Kuiper. The way to do it is very simple. First of all, you take this as is and you shrink it. It doesn't preserve the length. This is sub-solution, is below. And what do you do now? You start adding wrinkles. The length becoming longer. You add more wrinkles, and more wrinkles, and more wrinkles, and more wrinkles, until you basically reach to the original one. Another option is basically, can I basically embed this piece of paper inside a very tiny small ball without changing the length of arcs on here? You can basically keep doing that and then until it becomes too tiny, and then you put it inside the ball without basically tearing it, etc. But this embedding certainly is not very smooth. And the whole thing about Nash-Kuiper is how smooth is this embedding and so on and so forth. So they use ideas of this type to talk about fluids. So this is, in some sense, nobody can tell me this is really applied mathematics the way we teach it in universities. Okay? So therefore, we don't know where ideas are coming. So mathematics is one subject. There's no applied and pure. Okay. So earlier, our results were established by Schneermann and Schäfer. So I will skip this. This is a result with Bardos in which we prove lll-posedness in the space C0 alpha of the Euler equation. Namely, if the initial data is in C0 alpha, there is lll-posedness of Euler in 3D. This is a result of Bardos and myself. I will skip that. Special results of globus of three-dimensional Navier-Stokes. I'm going to talk about special cases. The first result is basically due to Fujita and Kato, which tells you if the initial data is small in H1/2, then you have global existence of Navier-Stokes. So there are some initial data where we have global existence. But then the initial data has to be small. Now, why you need the initial data to be small? The nonlinearity in Navier-Stokes, U grad U, so it's quadratic. The good guy, the viscous guy, is linear. So if U0 is like epsilon, the nonlinearity is like epsilon square. The linear is like epsilon. So epsilon can overtake epsilon square when epsilon is small. That's the idea behind it. Okay? But then it has to be small in which norm? Because I told you the norms are not equivalent. So the work of basically Fujita and Kato to know in which norm the initial data has to be small. For the engineer or physicist in this audience, when they look at this result, they say, wow, global existence, that's nice, that's great. But then the physicist engineer says, I don't care about it, it's boring. Why? Because it's a small Reynolds number. There's nothing interesting here, there's no turbulence. And indeed, but nonetheless, the machinery is interesting. But this is the first result. I will build on that. Another result is due to Layzhenskaya. She looks at axisymmetric flows. Namely, she looks at the domain. This is the cross-section of the domain, rounding, like basically like a bagel or like a donut or like a tire. So this is the cross-section. So axisymmetric with positive distance from the axis. So for initial data of this type, which is depending on R and Z, these are all axisymmetric. Then she proved in this case that you have global existence. So the solution depending on R and Z. Later with Leibovitz, Mahalov, and myself, we proved if you look for helical flows, namely you look into the pipe and solution which have helical symmetry. So every time you go n round, you go 1 over alpha step like that. So they are functions of R and this combination. Then you can prove a global existence for this. No, this is global. The only result with small initial data is Kato. Layzhenskaya and this for any initial data. So for helical, you have global existence. And now the question is, what's the idea? The idea is very simple. The idea is basically that these are functions of two variables. And I told you when I have functions of two variables, I can use the embedding theorem of L4. Effectively, they are functions not of three variables, x, y, z. They are functions of two variables. That's why you can prove it. But the vector field is three-dimensional nonetheless. So, the axisymmetric and helical flows, the vorticity stretching is non-trivial. That's what I'm telling you, vorticity stretching is overrated. And yet you have global existence. For as large as initial data as you want, for as large as Reynolds number you want, with this symmetry you have global existence. What happens if you have no viscosity? We don't know. So that's why in the limit with viscosity equal to 0, we don't know about this solution. There is a very interesting result, which is due to Caffarelli-Cohen and Nirenberg. The Caffarelli-Cohen-Nirenberg result states that if there is a singularity for Navier-Stokes, when you look in the four-dimensional spaces, namely space and time, the singular set in space and time has Hausdorff dimension less than 1. So it is less than a curve. So if you're looking for a singularity, if you want to see it with your eyes or experimentally or in the computer, whatever, good luck. Now, the result of Layzhenskaya follows from their result. Why? Because if you have singularity at one point, because of axisymmetric, you have a whole curve of singularity. Aha, but the singularity should be less than 1. Therefore, by Caffarelli-Cohen-Nirenberg, the result of Layzhenskaya follows. But Layzhenskaya work was before Caffarelli-Cohen-Nirenberg. So in that sense, she is safe. But our result with Leibovitz and Mahalov came after helical flows. If I take one point, there is singularity, I have a whole helix in which I have singularity. So therefore, our result follows from Kafarlik-Koenen-Berger. Not so fast. What if the singularity is at the axis? Oops, at one point. I don't have a helix at the axis. And therefore, it has dimension less than 1. So therefore, we are rescued, so there is a merit for the result. Okay? Just to basically tell you where the mathematics is playing, trying to understand what's happening here. We take in two-dimensional flows. Do the two-dimensional flows remain two-dimensional? This is really, it was a surprise to me. When we talk about 2D Navier-Stokes equation versus a 3D Navier-Stokes equation, we assume that the initial data is function of xy, and we assume implicitly that the solution remains function of xy. But when you talk about weak solutions which we don't have uniqueness, what if the solution decided to become suddenly function of x, y, and z? Of course, it is not intuitive, but I mean, how can you prove it? I don't have uniqueness. If I have uniqueness, then I don't need to worry about it. Or what if I start axisymmetric, but then the solution which exists would like to break this symmetry and stop being axisymmetric or stop being helical? And for the longest time until this work, all the scientific community overlooked this point. When we talk about existence in 2D and axisymmetric, the assumption is that the solution starts being axisymmetric and remains axisymmetric. So the result that we proved is the following. If u0 is a function of xy, then the Lerehov, namely the solution, weak solutions, which are having satisfied energy inequality, they remain function of xy. So the community is saved by the bell in some sense. That if you start function of xy, you should remain function. You cannot become function of xyz. This is a theorem. And similarly, if you start axisymmetric, you remain axisymmetric. Now, how about Euler? In the case of Euler equation, based on this construction of Delinis and Székely, which has infinitely, one can construct initial data which are function of xy, but the solution later becoming function of xyz. They bifurcate suddenly. They're becoming dependent on the third variable in a mysterious way. Again, this is basically most likely cannot be physical. So therefore, now you can start seeing this difference between Navier-Stokes and Euler, even at that level. And similarly with axisymmetric and so on and so forth. This is basically lead me to believe that in some sense we have to put some kind of like regulations. We have to regulate what is a player, what is not a player. And because viscosity is part of nature, we cannot really avoid it. Then, in my opinion, every solution of Euler which cannot be achieved as limit of Navier-Stokes in the absence of boundaries should be ruled out, cannot be a player. And this way, many of those solutions which have been constructed, namely with zero initial data, will remain zero. Otherwise, they cannot be a player. The same with these axisymmetric things. So even though they are mathematically beautiful, it's absolutely mind-blowing, beautiful theory, but nonetheless, it introduces us a new way to think about things. That's what I said. The journey of looking for a solution by itself is really interesting. So this is the ruling out mechanism that I mentioned about it. So I will skip this as well. There is another result which is very interesting, which is due to Canoni, Meyer, and Planchon. And when this result was announced in Paris in the 96, it was very excitement. And the result states the following. Suppose you take initial data, which is very oscillatory. Very large, but very oscillatory. Then you have global existence, okay? And now you ask yourself, so this means that global existence for Navier-Stokes with large initial data, that's a really big result. But then you ask yourself, why do you need it to be oscillatory? By the way, these people never formulated it this way. This is my Reader's Digest. I'm just basically did plastic surgery to the result, and I'm putting to you what's really happening, okay? So you take initial data, which is very, very large, but very oscillatory. And then you have global existence. So physically, because there are some physicists here, why do you need it to be very oscillatory? It's very simple. Because when the initial data is very large, but the oscillation is depending on the amplitude, then the viscosity, like the heat equation, boom, kills it in no time. It becomes small. Therefore, immediately the solution becoming small, and now you are back into small initial data a la Kato. So in other words, such initial data is in some sense small Reynolds number when you look at it in the right topology. Okay? So therefore, this result is again small initial data in some sense. Okay? So this I would like to skip this. What I want to do, I'll talk about stability. I will skip this. Rotation. Okay, what about rotation? So this is the Euler equation. And since we live in a rotating Earth rotation, what does the effect of rotation? Many geophysicists tells us that rotating fluid, it basically stratifies the fluid and make it more look two-dimensional. Oh, this is interesting. If I look at the 3D Navier-Stokes equation with rotation, then as you can see that if I do energy estimate, this is cross product, it's anti-symmetric, it gives you 0. If I take derivative, take these Hilbert space techniques that I am worshipping, it gives you 0. Therefore, this rotation term does not hurt me every time I talk about norms. And therefore, with rotation, without rotation, for me, if I'm naive and doing a priori estimate does not help. But geophysicists tells me, no, rotation is doing something good, in some sense, stratifying the fluid. And indeed, this is basically what this observation, which is first done in the mathematical level by Babin, Mahlov, and Nikolenko, in which they proved if you rotate fast enough, if you give me a time and initial data and I rotate fast enough, then I can guarantee you the solution remains living, or the lifespan of the solution is time t. If you want the lifespan to be longer, you have to rotate faster. Okay? This is really very interesting observation. The question is why rotation preventing this from happening? To do that or to see that, one has to take this example, which is the Burger's equation, which we know it blows up. If I complexify Burger's equation, I add rotation here and make change of variables, v equals e to the I omega u, then the v satisfying this relationship, one can solve explicitly and show that v is basically never blows up when omega is very, very large. But I would like to focus on this equation. There was a rotation in the u equation. After change of variables, it becomes like that. When I write this equation in the integral form, v equals to this. If omega is 0, look to this. Again, I'm going to put the hat of a physicist. V is the initial data. V is large. Therefore, I have v, vz. This is like large square. I integrate it in time. I have the left-hand side large. How could I make large square balance with large? Only if the time is very small. And that's what happens in Burgers. People prove for short time you have existence and uniqueness. Again, this is hand-waving. This is not proof, but gives you feeling for what's happening. And now I claim with rotation, when omega is not 0, and large enough depending on initial data, I have global existence. How come? Well, this is again for the students here in the audience. Look how beautiful is the following observation. The observation is something called the Riemann-Lebesgue lemma. What does Riemann-Lebesgue lemma tells me? That if you give me a nice function periodic, the integral of this against sine kx from 0 to pi, the limit goes to 0 when k goes to infinity. Namely, when you integrate a function against something very oscillatory, it becomes small. Fast oscillations make the quantity small. Omega large, this is a huge square. Omega large, when I average it, this huge square averaged out becomes mild, becoming weak. And therefore rotation preventing the singularity from happening by averaging process. And that's what happens in the Euler with rotation. Because there is no resonance between the Coriolis force and the nonlinearity. Then the rotation is in some sense averaging the nonlinearity, make it weaker and milder, allowing the lifespan of the solution to extend. So here basically where we use mathematics to try to interpret what the physicists are seeing. This is the interaction between the community. I think my time is, how much time do I have? I mean, or how much I passed, how much I owe you? I see there is 26, but this is maybe misleading. How much time do I have? I mean, before I start negotiating. I mean, let's ask the director here, or you, director. Yeah. Nobody wants to take a decision, so we are here until the morning. So, huh? 5 to 10 minutes. Okay, because I want to get into other aspects. So this is I explained to you. So how can the computer help? Can the computer help? And here, I pardon people who are doing computations, because I'm going to exaggerate. I say, this is the cartoon, okay? So how can the computer help? Because analytically, we don't know how to prove existence, uniqueness, etc. Can the computer help? Well, to understand that, basically, we have something called Reynolds number, which is the ratio between the nonlinearity and between the viscous term. The question, which is stronger? The bad guy, the nonlinear guy, which is causing instability, or the viscous, the term which is causing stability. So the ratio between them is dimensionless. This quantity called the Reynolds number. So in weather prediction, in the atmosphere, the Reynolds number is of the order like 10 to the power 8. In the case of the number of equations that I need to solve with the computer, will be like Reynolds number times 9 to the power, Reynolds number to 9 over 4. So in the atmosphere, when you discretize, you do finite differences in the equations of Navier-Stokes. In the atmosphere, if you like to solve exactly everything nicely with all the details because I want to know everything, okay? Then I need to solve algebraic system of 10 to the power 18 equations, linear system, which means I have a matrix 10 to the 18 by 10 to the 18 that at every time step I have to invert. Okay, I have problems inverting matrix 3 by 3. Imagine matrix 10 to the 18 by 10 to the 18. In fact, this is a whole field of mathematics called basically numerical linear algebra. Is how to invert matrices. There is a whole art of that. So there's another field. You see, it can connect to here. And all the biggest computer in the world, right now, all what they're doing, they are inverting matrices. That's what they do. Okay? So therefore, this is out of reach. Forget it. Okay? So for example, if you look for a flow around the car, which is the Reynolds number like 10 to the power 5, I need to solve 10 to the power 10 equations or unknowns. So the question is, how long does this take? If I would like to know exactly the solution for short time around flow around the car, not the climate, I'm not talking about the weather, only flow around the car for a short time. How long do you think it's going to take for the best computer in the world? And here I'm going to exaggerate a little bit, but I'm not really out of it because you have to keep updating the situation. So let's start a bet here. How long do you think it's going to take? 5 hours, 2 days, 3 days? How long do you think it's going to take? Just take a number.
Few weeks.
Few weeks. Let's start with a bet. 5 years. Who want to say more? 50 years. Who want to say more? 500 years. Supercomputer, the biggest computer. So I'm going to miss 5,000 years almost. Okay, this is the biggest computer. Maybe I'm going to be off a little bit, so subtract some norms, whatever, something. But it takes so long that in order to see what happens to the flow around the car, I wait and see it. I don't want to wait 5,000 years. I wish I could wait 5,000 years, but I will not be here. Okay, so therefore the computer to solve with all the details is hopeless. We don't know what to do. This is because I'm interested in all the details. But am I interested in all the details? Sometimes there are too much details. You don't need it. That's what statistics is all about, because we cannot handle all the details. We need to look for averages. So therefore, we have to look for basically some kind of like average quantities. So now, if you look for experimental data of turbulent flows in the channel, so this is the data, like the vorticity, the velocity of one component at one point. You see this signal. I think if I look at these signals, I think when I open the Wall Street Journal, I think this is maybe the fluctuation in the market. Okay? This same signal, if you go and basically a few hours later and see it, you get something which doesn't look, it looks like erratic and crazy, but you don't see that this and this are correlated, you know. However, if you do the probability distribution or the histogram of both those signals, you discover the same thing. And this is something which is like science. In some sense, even though the motion is turbulent and so chaotic, there is some kind of order within chaos. There is something nice. There is some features which is universal or nice and repeating itself. And that's the probability. Therefore, if you give up and you look for the histogram, the probability distribution, namely for averages, for statistics, maybe things are nicer. And now the question becoming, can we solve for the average? Unfortunately, if I average the Navier-Stokes equation, there's a product. We teach the students, we teach you, that the integral of product is not the product of the integrals. And therefore, I have problem, I have closure problem. So I don't have equations which are close to solve for the average. And that basically makes us mathematicians try to think, can we show that there is some kind of measure, probability measure, reflecting what's happening for the Navier-Stokes equation? I would like to jump into the last transparencies. And this is something called statistical solutions of the Navier-Stokes equation. And the question is, are there probability invariant measures associated with the solution of the Navier-Stokes? These are called statistical solutions. Can we find a solution which is like mimic this probability distribution associated with solution of Navier-Stokes? In fact, this work started by Foias and Prodi in 1975, and they proved there exists statistical solution, in particular in two-dimensional case. And in fact, there are infinitely many, not only one. And now the question becoming, what would be the physically relevant ones? So we have to go back to the engineers and to the physicists and start basically select which one cannot be a player and which one should be the player. In particular, one of the challenging problems for some of us doing in mathematical analysis in turbulence is basically trying to show that of all these zoo or infinitely many probability distribution, there is one which is completely supported on the attractor, fully supported in the attractor, which is most likely will be the most physical, and therefore it will be the one reflected by the histogram. Is there such a one? How do we select it? What are the criteria? Here we need not only equations, and this is basically the point. I need not only equations, I need in addition some principles, which is physical principles like maximizing energy dissipation, minimizing this, and that's where we need to interact with physicists. So if you'd like to do applied mathematics in a sense of making an impact in the field, you got to basically interact with other scientists from other fields. Thank you very much. This is basically was the last transparency.
Okay, questions? Would you take some questions?
I'm willing to take questions.
And there are...
I cannot guarantee answers, but...
I have one question. Sorry. Okay. So in computer, if you solve an equation, there would always be error because of finite lattice spacing or something like that. So how can we use numerical solution to prove the existence of a solution? Is it?
Well, there are some areas of mathematics which is called computer-assisted proofs. I'm not really expert in that thing, but I think at least in this problem that we have at the moment, the final resolution that we need to achieve is not at hand. So, but there are some areas of mathematics. So I basically, mostly about ODEs and things along this line, with something to do assisted, like what's called computer-assisted proofs. I'm not expert in that, and I rather not comment on that.
So this question about the probability distribution that you asked, that you mentioned at the end, it must be related to the type of noise actually that is there in the system, right? So is that a more accessible question?
This is a question which is extremely relevant. The question is where is coming from? Okay, I give you the equation, I give you Navier-Stokes. Where is the noise? Of course, one can basically have a philosophy of the noise coming from that the parameters are not perfect, or the apparatus is not perfect, etc. So if you would like to extend and basically solve a problem which is accessible, you say, well, let me put right-hand side, which is a force, which is random. In this case, there are a whole theory. Basically, lots of people work like Mattingly and Hairer, and before that, Wenan A and Sinai, and many other people, in which they proved that in case you have adequate white noise as a force of the Navier-Stokes, the process is stochastic process has a unique ergodic invariant measure. Now the question is, what does this do with all these infinitely many measures? In my opinion, basically this noise make you bouncing from one invariant measure to the next, because convex combination of invariant measure is an invariant measure. And therefore the noise keep pushing you from one state to another until you basically settle down and average. So mathematically, yes, there is such a result. The question, is this physical or not? How is it related to the physics? Because as I said in the very beginning, Navier-Stokes never come with right-hand side forcing. You force the Navier-Stokes by boundary conditions or by coupling to the temperature, not by force. So where is the force in the right-hand side being noisy? I don't know. The thing which is I asked along your lines of your question, I asked the expert who are working in this, what if you put noise in the boundary condition? And nobody knows how to deal with it. At least not yet. Maybe the tools are not available yet, because this is more relevant.
I have a, may I ask a weaker question related to that? One thing which many people who are doing turbulence research have argued about for quite a long time is about these statistical solutions, what you call the statistical solutions. You take a particular class of flows. Take, for example, you talked about an axisymmetric jet. Take an axisymmetric jet. Are the statistical properties of such a flow at sufficiently high Reynolds numbers, or in the limit of the Reynolds number tending to infinity, universal and independent of initial conditions? Suppose you make a jet. You blow the jet there. By a given Reynolds number, are the statistical solutions universal?
Well, this is a very difficult question. In other words, you're asking me what happens to the statistical solution. Do they converge at all to anything as the Reynolds number go to infinity? I don't know, because as I told you, especially in the presence of boundaries, I cannot even in 2D show that solutions of Navier-Stokes converge to solutions of Euler for short time. When we talk about statistics, it means they have to converge somehow in the average for infinite time. So this is a difficult question, but certainly it makes sense.
If you're talking about a jet,
but even 2D, I mean, nothing to do with the jet. I mean, like even 2D in bounded domain, simple problem. If I look for the invariant solutions of Navier-Stokes, and I have infinitely many of them, which one of them converge to where? I don't know. It's a very difficult question.
Any other questions? Okay, if not, let's thank Edriss for a great talk.
Thank you very much. Thank you.
Please join us for the high tea outside, where you can, of course, ask more questions to Edriss.